is part of the course on subRiemannian geometry. I will now quickly revise some notions of metric geometry. In particular, I will discuss the abstract notion of length of a curve in a metric space. Let's see. I will go very fast in this review of metric geometry because I expect that the students already saw some theory of metric spaces. So if M is a set and we have a function from M to M, value into 0, infinity, where infinity might be included, is called a distance function. If so, we have the first property, which is the function is positive unless 2 points are the same. So the 2 points at distance 0 means that they coincide. So this is positiveness. The second one is the symmetry. So we have that the distance from, so this value is called the distance of x and y. The distance between x and y is equal to the distance of y to x. This is the symmetry. And the third one is the triangle inequality. The distance between x and y is less or equal than the distance from x to z plus the distance from z to y. Okay. If you have these conditions, then M is called a metric space. Okay, we will just write M when the distance t is understood. Distance functions are also called distances, but it's better to really call distance the value that the distance function obtains. Okay? Distance functions are also called metrics in general, but we don't want to confuse them with the Riemannian metrics that might appear later. Okay, so I will try to stick with the terminology of distance function. Okay, so whenever we have a distance function on a set M, we can define open balls. Open balls may be better to write the predicts where the distance function is okay. It would be better to also denote the metric space that we're considering. To be even more precise, I should write comma t here, but I don't. If t is understood, then this is q in M, such that the distance between p and q is less or equal, is strictly less than r. So this set is called the open ball of center p and radius r. Okay, so these sets give the topology for the metric space. We can also define the closed balls that we will denote with a bar on top of the B, and these by definitions are the set of points for which the distance is less or equal than r. Okay, so these are called closed balls. So this is the closed ball of center P and radius r. Let's pay attention because there are examples where the closed ball is different than the closure of the open ball. Okay, it's definitely contained, but might be strictly smaller. Okay, so now what is a curve in a metric space? So a curve on a metric space M is a continuous curve as gamma from I into M, where M is equipped with the topology given by the open balls, where I is a connected subset of R. Okay, so which means these are also called intervals. And I stressed that this interval might be open, closed, half open. It could be either bounded or unbounded. Okay, now if instead I is a compact interval, we say that gamma is a curve from gamma of A to gamma of B, or that gamma joins gamma of A to gamma of B. Okay. Now, if gamma is a curve, let's define its length. So let's say AB is the domain. So say we have a curve in a metric space. Then, by definition, the length of gamma, so length gamma is the supremum of all these quantities. You consider a partition of the interval 0, 1, AB into points. So you say I go from 1 to k. So k is the number of points we choose. This point goes from go from A T0 or T1, T1 less than T2 less less than Tk, which is B. Okay, so what we do like this. So we have this length, we consider points along the curve, and then we take the distance between consecutive points, we sum them up, we take the supremum. So this is the length of a curve. Okay. Now, some properties and or definition first, maybe. A curve that has finite length, by definition, this is called rectifiable. Then a property that if I reparameterize the curve, I obtain the same length. So with beta reparameterization. So the homomorphism between intervals. And if gamma is then another definition. Gamma is parameterized by arc length. In the definition, if and only if the length of gamma restricted to every interval has length exactly the length of the interval. So for all T1, T2 in AB. Okay, every curve has a emits a reparameterization by arc length. So every rectifiable curve. So if this is finite, then one can reparameterize having this property. Okay, now let's see some deep results on the notion of length. So we have a first important theorem. It's called semi-continuity of length. and it states the following. So if you have a sequence of curves converging to another curve pointwise, and they are rectifiable, or also actually makes sense when the length is infinity, then the length of gamma is less or equal than the limit of the length of the curves. Okay. Another important theorem is Ascoliar-Zela compactness theorem, which says that so if you have a compact metric space and you have a sequence of curves such that the length of them is uniformly bounded for all j, it's less than some L, fixed finite number, then up to reparameterization, we have that the sequence converge to some curve uniformly. Okay, I will not present in this video any proof of this these two theorems, but you can find the proof in the lecture notes. You find the link to the webpage of the course in the description of this video. From these two theorems, we get very easily an important theorem, which is called the existence of shortest curves. That says that if you have a compact metric space and you fix 2 points in this metric space, and let's say that at least these points can be at least connected with some curve sigma 0, curve from P to Q with finite length. Okay, no, not sigma 0. Okay, assume that they can be connected with a rectifiable curve. Okay, then there exists a curve from P to Q that is the shortest, or a shortest. So, namely, that its length is equal to the infimum of all possible curves from P to Q. Obviously, all these curves are meant to be valued into n. Okay, let's give the easy proof. Okay, it's a consequence of semicontinuity and Ascoliar-Zela. So, take a sequence of curves that converge to this infimum. So, let gamma j sequence curves from P to Q such that the length of gamma j is a sequence that converge to that infimum. Okay, notice that the length of gamma j is I mean, since sigma is a competitor, then these lengths are all less than sigma, L of sigma 0 plus 1 for j large enough. So what you have is that the sequence has uniformly bounded length. Therefore, by Ascoli-Zela, we have that the gamma j converge to gamma uniformly up to reparameterization, but length remains the same. Same length. Okay, so now they converge uniformly. In particular, they converge pointwise, and then we have the semicontinuity. Semicontinuity implies that the the length of gamma is equal to the lim-inf of the length of the gamma j, which was constructed to be equal to the infimum. But of course, the length of gamma is a gamma, in particular, since all this sequence gamma j went from P to Q, also the limit goes from P to Q, so it was one of the competitor. So we have that the length of gamma is at least equal to the infimum, which implies that gamma realizes the infimum. End of the proof of the fact that in compact metric spaces, we have existence of shortest curves. Okay, now we are interested in spaces where every 2 points are connected with at least a shortest curve. So first of all, let's give this definition. So let's say that MD is a metric space. Then I will define what's called the inner distance. The inner distance dl between P and Q is equal to the infimum of all length gamma when gamma is a curve from P to Q. Okay, so in general, we don't know, it may not be true that this infimum is realized, and this might not be equal to the distance function d, but if d coincides with this dl, then by definition we say that MD is a length space. Length space, because what we mean is you can define the distance function as the infimum of length. Of course, this length are defined up to via the distance t. Okay, another name for is also a path metric space. Metric space. All right, then another definition. So if exists gamma curve from P to Q that realizes the infimum, not that realizes, that for which the length is equal to the distance function dpq. Then, as a definition, we said that gamma is a geodesic. Then, if instead, the same but with length equal to dl pq, we say that gamma is a length minimizer. Okay, so if a space is a length space, then being geodesic is the same of being length minimizer. Okay, now we are interested in length spaces, and we are interested in the case where the really all points PQ in M that exist a length minimizer, and D is length space. So D is a length space. So this by definition, we say that then MD is a geodesic space. Okay, now I will present some criterion to say when a length space is a geodesic space. Okay, so more or less what we need is some local compactness. but I will ask a little bit stronger assumption, because this is what we will have in our setting, and that's good enough. So if you have a metric space, we said that the metric space is boundedly compact, or proper, this is another term used, if bounded sets are pre-compact. Pre-compact means the closure is compact. Equivalently, if closed balls are compact. So here is the theorem that we will use in the setting of subRiemannian manifolds. So if you have a boundedly compact metric space, there is also a length space, then it is a geodesic space. Now the proof is very easy. So to fix P and Q, we have to find a geodesic between them. So in space. So the fact that it's a length space implies that there exists some curve. So the distance is realized by as the infimum of the length. So in particular, there is a curve with finite length. So curve from P to Q with length. So maybe we don't know yet if it's equal to the distance between P and Q, but if I put an error, say 1, then I can find a curve like this. But now note that if sigma is another curve from P to Q, if the length of sigma is less or equal than the length of gamma, then the image of sigma is contained in the ball center P and radius the distance PQ plus 1. Okay. Since the length is bounded by this number, which is bounded by this, so when you have a length bounded by this number, you start from P, you cannot leave the ball, right, of distance, of radius that length. And what we know that this object here, so let's close it now, such a way that, so now this is compact. Okay, so what we have to infimize are curves in these compact sets. And we know that there exists a shortest curve, right? So this implies that we have existence of shortest curve for compact metric spaces. And this concludes the proof of the fact that bounded compact length space is a geodesic space. I will now present another equivalent definition of length of a curve as an integral of a metric derivative. This will be useful in the calculations, even in the Euclidean setting. So let's say we have a metric space, and we have gamma, a Lipschitz curve. Lipschitz curve. So we define the metric derivative. This is a symbol, so it's the derivative h goes to 0. The derivative of the distance between gamma t plus h, comma gamma t divided by h. Okay, so if this exists, so if this limit exists, it's called metric derivative. Metric derivative of gamma at t. Okay, let's pay attention because we haven't defined what is the derivative of the curve. So this symbol does not make sense. You should consider all this notation as a whole, a symbol, whole terminology. Okay, so we define the length of the derivative without having defined the derivative. Okay, so we call it the metric derivative. Good. So here's the theorem. So remember, we're assuming that gamma is a Lipschitz curve. Then, so first of all, the metric derivative exists almost everywhere. So for almost every t in the respect of the Lebesgue measure. And second, the length of the curve is exactly the integral on the domain of the metric derivative. So this is the theorem we're going to prove now. Okay, proof. So a small observation. So from the triangle inequality, we have that for all points in the space, we have that so the distance between gamma t plus h, comma gamma no, let's put y here, minus the distance from gamma t and y. This is less or equal than the distance from gamma t plus h, comma gamma t. Okay, so this is just the reverse triangle inequality. It's triangle inequality, right? If you bring it this on the other side, this is the normal triangle inequality. So we have this, and of course we can even swap the role of this two guys, so we can even put absolute value. Okay, so we have this property. Moreover, we have equality if we choose y equal gamma t. That's clear. Okay, so now what we do, let's consider y ranging on a set that is dense in the image of gamma. So take xn, a countable dense set in the image of gamma. And now we give a name to this function when here we put xn. So note phi n of t, the function distance from gamma t to the point xn. Okay, so let's rephrase this property here. Say that so if we take phi n of t plus h minus phi n of t, then we get something that is always less or equal than the distance between gamma t plus h, comma gamma t, right? But now since we are letting the yn vary, so they can get arbitrarily close to gamma of t, and therefore which means that if you take the supremum of these quantities, we really get equality. So this is going to be a formula. This is what we're going to use it soon. So let me give a name. So the symbol, okay. So this one, triangle. Okay. Moreover, what we have, okay, the function, each function phi n, this goes from the same interval of definitions I of the curve to R, okay? And this function is Lipschitz. because the distance from a point, so gamma is Lipschitz, and the distance from a fixed point, this is always Lipschitz with constant 1 in each metric space. So this is Lipschitz with same constant as gamma. Now, okay, so this is a Lipschitz function from an interval to R, and then from the Rademacher theorem, the Rademacher theorem in one dimension, we get that phi n is differentiable almost everywhere, and the function is actually the integral of its derivative. Okay, so we can consider the derivative of these functions, take the norm, and take the supremum in n, and we define this to be m of t. Okay. Now the claim, so this m of t for sure exists. Okay. Now the claim that we're going to prove is that m of t is equal to the metric derivative for almost everything. So in particular, the metric derivative exists almost. Okay. Let's prove this claim one inequality at a time. So let's start with this one. So what do we do? This is the easier one. Okay. So remember, so we have phi of n of t. Now the derivative is, this is for almost every t exists. So it's phi n t plus h minus phi n of t divided by h. Let's put absolute values. Now, remember that we have the phi n, they're always less or equal than the distance between the points. So let's use this one here. Oh, sorry. Second. Okay. Okay, let's put it here. So this is less or equal. Then, okay, we don't know in general that the limit exists, so let's put liminf of distance between gamma t plus h minus, comma gamma of t divided by h. Okay, so if for the definition of the metric derivative, if I take the liminf, I get something greater than phi n dot. Then of course, passing out to the subprimum on n, I get this inequality. Okay, the other inequality, so a bit harder. Okay, so let's start with this observation. Let's take the distance between gamma t and gamma s. Okay, now this again by the condition delta, this is equal to the supremum in n of phi n t plus t comma, no, sorry, minus phi n of s. Okay, now each phi n is differentiable, so by the theorem of calculus have that it's the integral from s on st of phi n dot. I can move the absolute values inside. This is phi n, and now okay, and from the first part, so we proved that phi n is smaller than but then by definition so, and this is equal, yes, so this by definition this subprimum is less than the integral t of m. So okay. So I want you to notice something, that this integral is really finite. And why is this? So I want to notice that m is actually in L infinity of the interval I. And why is this true? Because so the we said that the Lipschitz constant of phi n is less or equal than the Lipschitz constant of gamma, and therefore each derivative, so a derivative is almost always less than the Lipschitz constant. So each of these functions is less than the Lipschitz constant of gamma, and therefore the subpremium has the same bound. Okay, so this integral is finite. Okay, so this would be an important formula. Maybe another symbol. Okay, we're going to use it soon. All right. So let's continue. So now what we have, so let's consider the distance between gamma of t plus h and gamma t divided by h. From what we saw, this is less or equal than the average integral of from t to t plus h of m. Now, so this is exactly this equality here. So I put s equal to t plus h and I divide it by h. Okay, now if I take t to be a Lebesgue point, or for m, then I have that the average integral converges to the value of the function. So if t is a Lebesgue point for m, and almost every point is a Lebesgue point for m. So we have this limit. Okay, so what do we get? We get that then the lim sup of gamma t plus h gamma t divided by h, this is less or equal than mt for almost every t. Okay, and therefore we have also the other bound, that the metric derivative is less than m. Here we proved instead that the metric derivative was greater than m, that's primo. Okay, so in conclusion, we get that mt is equal to gamma t for almost every t. So we proved that the limit exists. So in particular, this thing exists almost surely. Okay, now what we have to prove next is that we have to prove that the length can be calculated as the integral on I of gamma dot. Okay, again, let's prove the two inequalities. Start with a simpler one. So let's take, in the definition of length, let's take a partition. So they said that I is the interval AB. And then we take, so 8 equal to 0, then we have t1 up to tn, which is equal to p. And then we have that the sum of the consecutive distances, ti minus 1 gamma ti, I from 1 to n, this by the condition, I'm going to use this one. So I'm going to bound them with the derivative, with the integral of m. So
this is less the sum of the integral on this ti minus 1 ti of m. And now I can just put together all together this interval, and I get the integral from a to b of m. And we saw that okay, but m is the metric derivative. Okay, so one inequality is done. Next one. Okay, for this, let's take epsilon greater than 0 and take some n natural number such that if you define h to be b minus a divided by n, this number gets smaller than epsilon. Okay, and then we set ti to be the point a plus I times b. So what we have done is the following. So we have the interval a, b, and then we have consider points. This is going to be Tn in such a way that each of these distances is less than epsilon. Okay, now there is a small trick. So we calculate the integral from a to b minus epsilon of the distances gamma t plus h, comma gamma of t in dt. Okay, now of course we can split this integral along the sequence of points that we chose. This is the integral, the sum of I from 1 to n of the integral from ti minus 1 to ti of the same function, gamma t plus h, gamma of t in dt. Okay, so now you see in every integral here, we are going, so t, the variable, is going from these two extremes. So it means that we are integrating on each interval. Okay. Now I'm going to change variable, and I'm going to call this this length. Let's call it s. So this integral is the same of integrating from 0 to h. Okay, let's make a change of variable here. Say s is equal t minus ti minus 1. Okay, so now this will be gamma of ti I minus 1 plus s, gamma ti plus s in ds. Okay, this is change of variable. Another thing. So here I have integrated only up to b minus epsilon. So here I don't have to include the last index. So I can put here n minus 1. Okay, so this I from 1 to n minus 1. Now I'm going to swap the integral and the sum. So I'm going to swap. And now what I see is that, see, I'm summing on the consecutive, so fixed, think that s is fixed. So now what we are doing is the following, you see in the picture. So I'm translating on by s, and then I'm adding this distance plus this distance plus this distance and so on. And at the end, you see, that's why I removed this last the last interval. Okay, so now if I sum, what do I obtain? I obtain that, so there's the integral, and then the sum of those elements. This is less than the length. The length is the sup. This is the length of is less than the length of gamma, integrated. So this is h times the length of gamma. Okay, now we are ready to conclude. Okay, so now, yes, so let's integrate from a to b minus epsilon the metric derivative. So this is by the definition of the metric derivative. This is the derivative of gamma t plus h, gamma t divided by h. Okay. Now I'm going to use Fatou's lemma to swap the limit and the integral. I have the integral from, sorry, this was b minus epsilon of the function. And now I'm going to use what I just proved, that this integral, okay, is less than the length, so I'm going to divide by h and obtain that this is less or equal, just before, of the length of gamma. So this proves the missing inequality. So we saw that, therefore, these two objects, so this is true for every epsilon, so it's also true for epsilon equal to 0. So the integral of the metric derivative coincides with the length.
If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.